Hello guys, I am Wian from P05. Today I'm gonna present my medical electronic presentation video. This is my circuit. It is a biomedical signal processing system used in the stethoscope to acquire the sound of the heartbeat. In this video, I'm gonna explain how the biosignal from our heartbeat pass through this circuit to become a sound that we can hear. There is 4 stages the signal had to pass through. Stage 1, preamplifier stage from test point 1 to test point 2, and stage 2, closed loop inverting amplifier stage from test point 2 to test point 3, and stage 3, active filter stage from test point 3 to test point 4, and finally the stage 4, which is audio amplifier, which ends at test point 5. Stage 1 is the preamplifier stage. The microphone in the stethoscope pick up the biosignals and convert it to electrical signals. So as the nature of the biosignals, those signals are very weak, often in just a few millivolts. So we need to preamplify those electrical signals to be strong enough for further processing. So in this stage 1, we gonna preamplify those electrical signals. First, the coupling capacitor C1 blocks DC voltage while allowing AC signals to pass through. Then the signal enters IC18, which is part of IC TN072. This is a dual noise GFET op-amp. It's a fixed gain closed loop non-inverting amplifier. R6 and R5 forms a voltage divider supplying IC with 4.5 volt, and it allows op-amp to work in a single supply mode. R2C2 and R3C3 forms bandpass filter. So passband gain formula for non-inverting amplifier is 1 plus R2 over R3, and finally we got a gain of 23. In this part, since we are only using single supply mode, it will cause the negative cycle of the AC signal to be clipped off. To prevent this, the voltage divider R5 and R6 also functions as the level shifter, and it provides the virtual ground of 4.5 volts for AC signal to swing around. So the amplified AC signal is riding on DC offset of 4.5 volts, and it is passed through C4, another coupling capacitor, and hence block the DC signal offset. So here in this table, we can see as the frequency increases, the gain also increases. And we can see the maximum gain of 22.45 or 27.02 decibel with the maximum output of 4.49 volt at 100 Hz. So after 100 Hz, the gain decreases finally. So based on the frequency response curve here, our maximum gain is 27.02 decibel. So by 3 decibel down, we can get our two cutoff frequency low and frequency high. Frequency low is 30 Hz and frequency high is 14 kHz. So from this value, we can calculate our bandwidth. Here in this video, I connect my probe to the test point 2, and then I set my function generator at the 200 millivolt and 200 Hz. Then I got output voltage of 4.8 volt. And when I change my function generator to 1 kilohertz, my voltage dropped to 3.36 volt or 3.44 volt. In stage 2, the amplified signal enters IC1B, which is also a part of the TN072 IC. So this op-amp is patched as an inverting amplifier using a negative feedback loop. So the signal enters the negative terminal while the voltage divider R9 and R10 supplying 4.5 volt through the positive terminal. The negative feedback loop amplifier means the portion of the output voltage is sent back into its negative input terminal with the phase inversion of 180 degree. The output waveform will be 180 degree out of phase with the input waveform. P1 potentiometer or the 100 kilo ohm trimmer controls the feedback signal. And that potentiometer can reduce the overall gain of the amplifier. And R9 and R10 also found as the level shifter, also providing the voltage and the virtual ground for the waveform as in the stage 1. And this stage can be used to stabilize the waveform and adjust the intensity of the waveform. So here I put my test probe to test point 3, and then I adjust my trimmer, and I use my function gen for 200 Hz and 200 mVp. Now I got output waveform of 4.98 volt. which is the designer output of Pipeboot. Then the stage 3 comes. The signal passes through C5. C5 blocks DC signal and enters into IC2A of ICTL072. The IC2A is patched as a Salanki second order low-pass filter. R7, C7, and R8, C6 forms the second order low-pass filter. R11 and R12 forms the voltage divider and hence acting as the level shifter. Hence, we can calculate the cutoff frequency. And here is the cutoff frequency formula. Fc is equal to 1 over 2 pi square root of R7, R8, C7, C6. And hence, we got the cutoff frequency of nearly 996 Hz. And the bandwidth is the difference between frequency low and frequency high. Frequency low is 0 Hz, so we got a bandwidth of 996 Hz. The Salanki filter, the Salanki order filter is the unity gain filter. So here, as you can see in the table, the voltage input with the frequency of from 20 Hz to 500 Hz called the unity gain. But the frequency about 500 Hz, they are called, they are ruled out very sharply. So this way, the Salanki filter can filter out the high frequency noises of the signal very effectively. So as you can see here in the frequency response curve, my bandpass is at 0 decibel. So to get my cutoff frequency, I need to 3 decibel down. So after 3 decibel down, I got my cutoff frequency at 1 kilohertz. So when I calculate bandwidth, I got the bandwidth of 1 kilohertz. So here when I put my test probe to test point 4 and then applying frequency of 200 Hz, I got the voltage output of 4.8 volt, which is the unity gain. But here when I apply the frequency of 1000 Hz, which is the outside of our passband, it is no longer the unity gain and my voltage drops. In stage 4, the signal waveform passes through the CH, the coupling capacitor A, to filter out the DC signal. And hence, it enters the third IC, LM386N, which is the audio amplifier that drives the speaker. So the function of the stage is to power up the waveform to be strong enough to drive the speaker. So it works. The IC works in the single supply mode internally, so we don't need to provide it with any voltage. So it is the only op-amp that drives current to power up the speaker. The capacitor C15 filters out the high frequency that is above 40 kHz. And the capacitor C13 blocks out DC signals, allowing AC signal to pass through. So the waveform will enter the trimmer P2, where pin E has the full amplitude of the waveform and pin A has 0 amplitude. So we can get the output voltage of 7.2 volts. We can adjust the volume of the microphone by adjusting the trimmer P2. So here, when I put my test probe to test point 5 and after adjusting my potentiometer, I got the clear and distorted waveform of 7.12 volt. So this is the end of my presentation. Thank you all for your watching my video and your patience.